Very good morning. Am I audible?
Yes, sir.
Are you able to see the screen?
Yes, sir.
Yes, sir.
Okay. So let's start today's lecture. We have done uh, the things related with the vector fields, how to integrate, and in particularly we have seen the line integrals, and we have also seen one of the application of line integral of vector field is given by means it can actually help you calculate how much work done had happened when a force is applied, okay, to move a object along a given curve C. Okay? So there are various ways to represent this total work done. So this dr, if we have seen, this is also that this tangential vector t ds. Okay? So S is the arc length parameter. Okay, this dr and tds are the same thing. Okay, right. So we have seen this. So let's so if so this is we have also denoted by capital W. Okay, so total work W is also the notation for work done. Okay. So this is one example. Evaluate the line integral of vector field F along the first quarter of unit circle in the first quadrant. Okay. So here everything is ready-made. Okay. So the given vector field is so I'm just talking about the solution of the ball. So that the given force is equals to x square I minus x into y j, and C means you are moving along the first quarter of unit circle in the first quadrant. So you have unit circle, and so when I already mentioned, when orientation is not given, okay, it is understood that it is positively oriented, means in an anti-clockwise direction. Okay, right. So, and you know, the parameterization of this curve C can be also written that is going to be x equals to cos t and y equals to sin t, cos t I plus sin t j, and where t is also now first quarter of the circle in the first quadrant, so from 0 to pi by 2. So 0 less than equals to t less than equals to pi. So you have every information now. Okay, and now you can find out how much work done had happened. So for that you need dr. So from above you can certainly find dr. It means you can say total differential. Okay, and then our vector. So in the I direction, in the j direction, so it's going to be minus sine t. I in the x direction, cos t derivative is minus sine t. And in the direction of j, it is cos t j dt. dt is, this will be the dr. Now, so now you have f. Also f you can write as x square I minus xyz. So x square, x is cos t. So it is cos square t I minus x into y, so cos t into sin t. If we have done this, anyway. So now you have to use that, you have to take the dot product of them. So now this and this applies. So now this implies f dot dr is equals to, so cos square t time minus sin t. So minus cos square t sin t. Here also minus cos square t sin t. So that is minus 2 cos square sin t and t. So therefore, the total work done along the first quarter of circle C is f dot dr, that is equals to integration 0 to pi by 2 minus 2 cos square t sin t dt. Now you know cos t derivative is minus sin t. So derivative is sitting, right? So it is going to be by 3 by the cos cube t, right? And it's a 0 to pi by 2. Now minus sin t dt is getting to the cos t derivative is minus sin t dt. Now upper limit minus lower limit. So that is going to be 2 by 3 cos cube t, cos cube pi by 2 cos pi by 2 0 0, and cos 0 is 1. It's going to be minus 2. Right? So this is the line integral of this vector field. Okay. Yeah. So this is the final value. That's going to be minus 2, right? Okay. Now we have learned one fundamental theorem in for integral calculus for function of single variable. Okay. So what was that? Is if you recall, I give you the important things from there. So fundamental theorem for integral calculus. Okay. So in the case of single variable, what was that? Is f is continuous, right? On closed interval AB. Then you have defined this f of x as integration a to x f of t dt. And you know f dash of x is equals to f of x. F is continuous and f dash of x is equals to f of x. So therefore, so this implies this is for all x in closed interval AB. Okay, so this implies as integration a to b f of t dt is going to be capital F of t minus f of t. Very fast. Means your objective was to find out the antiderivative. Okay, but which is sitting here of this, right? Okay, so this was the fundamental theorem for integral calculus. So the generalization of this is here. So you will also see. So in the place of now derivative, what you can expect in vector calculus is a gradient. Okay, so this is what is present here. Gradient of f dot dr. Okay, so these you are actually working with the gradient field, gradient vector field. Okay, right. So then you will apply the lot of concept, means like if the field is conservative and so on. Okay, then also that will also tell you that path independence is something we are going to learn soon now. Okay, So we have left that concept, right? Path independence means we have seen if you reach from one point to another point along different paths, that may lead to different values of the line integral. Okay, but in special cases, it will not happen. You will reach any longest path or any smallest path. The value of the integral will be the same. That is called as roughly as path independence. Okay, right. So I can read this now very quickly, the fundamental theorem of line integral. So let C be a smooth curve. I hope this is now very much clear. What do we mean by smooth curve? Means you have dr by dt is continuous and that magnitude is non-zero. Velocity magnitude is non-zero. Okay, so that will be said, then the curve is to be called as smooth curve. Okay, now so let's have this is a parameterization of means general one for the closed interval a to b. Now suppose you have this is a starting point and this is the ending point of the curve. Okay, so it's the C here is, let's say, x1, y1, z1, and it is reaching to x2, y2, and z2. Okay, now that is what this is means this r at a is at t equals to a is a starting point, and at t equals to b it is a ending point. Means it's increasing, as you can see, in the sense that it is moving from t equals to a to t equals to b. Okay, right. Now let f be a function whose gradient vector is continuous on a domain containing C. So this is what required, right? Gradient vector should be continuous. Okay, so gradient is you can always obtain a gradient for a scalar value function f. So that is gradient of f dot dr. That can be evaluated directly by final means f at final value minus f at initial value. That will give you the integral value. Okay, right. So in other words, suppose we have already learned that when we say a field is conservative, okay, we say we have learned that concept, right? Conservative means so the conservative fields means suppose somehow you analyze that f is conservative, means there is a scalar valued function f such that f is equals to theta. Okay, right. So now what it will tell you now? Now that if this happens, then this implies integral c f dot dr can be directly evaluated at f at the starting point x1, y1, z1. Sorry, end point x2, y2, z2 minus start f at starting point. Moreover, so say particularly if C is a closed curve, what will happen? So if C is a closed curve, then end point and starting point is initial point, both will meet. Then what we have this integral C f dot dr. In this case, when the field is conservative, that is 0. Along any closed curve or closed loop, you can say. Okay, so if the field is conservative, means there is a scalar valued function f such that f is equals to grade f. Now the fundamental theorem for line integrals tells you that integral c f dot dr is f of x2 comma y2 comma z2 minus f of x1 comma y1 comma z1. Now whenever the C is a closed curve, means end point and initial point both are the same. So functional values at both of that point are the same. So that's going to be 0. With this minus this. whenever you use it. So this is also one other way to look at the conservative fields as well. Okay, sometimes this also can be understood as the conservative field. Okay, whenever this happens, means what along any closed curve C, if f dot dr is 0, then also you'll say it's a conservative field. Okay, so this will also sometimes becomes the definition, or you can say both things are equivalent. Integral C f dot dr equals to 0 along any C along every closed curve C is equivalent to say that f is a conservative field. And hence, it also says that integral C f dot dr equals to this, means along any curve, means this also will say that path independence also will be coming into the picture here. Okay, so path independence, conservative fields, and the line integral along a closed curve C is vanishing along any closed curve C vanishing, then I will say is it means all these three statements are equivalent. What do we mean? That's what we mean from here. Okay, right. So if you have any question here, you can ask. Okay, no questions. So let's proceed now. So this is so we have to only read this definition now. Path independence. Okay, so let F be a field defined on an open region D in space, and suppose that for any 2 points A and B and D, the work done in moving from A to B is the same over all paths from A to B, then this integral is path independent. So roughly you have a domain D, okay, over which this vector field is defined. Now you choose any 2 points A and B inside this. Okay, so you can reach to A to B along any path. Okay, that line integral value, you take this is C1, this is C2. You may also have one straight line joining these 2 points, that's C3. So that integral C1 f dot dr same as integral C2 f dot dr, also same as integral C3 f dot dr. So this is what we mean. If you take any curve joining these 2 points, the line integral value remains same. That will tells you the definition of path independence. Okay, so it is this is what it's written here. In other words, we say that a line integral is independent of path if and only if you take any curve C dash that is lying in the domain and having the same initial and end points as that of C, we have integral C dash f dot dr equals to integral C f dot dr. Now, as I told you about the path independence, integral C f dot dr is 0 along any closed curve C and conservative field. All these three statements are equivalent. So you can also talk about the path independence in terms of the closed curve. So suppose you have the following line. So if let's say I say that, suppose I'm giving you this statement that integral C f dot dr equals to 0 for any closed curve C. Okay, then I say that this line integral for any closed curve C, okay, then I say that this line integral C1, you can say, or instead of this, I write A to B f dot dr is path independent. Can someone give the hint here? How will you proceed? So A to B, B are 2 points. Okay, A can assume as a initial point, B as a terminal point. Okay, in the domain. Let me help you. This is A, this is B. Okay, is path independent. So let's take this is C, or this is C, or you can say C1. Can someone give the hint?
So that means another curve C2 will be there, and it will both will form the closed curve.
Okay, good. So means from A to B, you can draw another curve C2, let's say. Let's any curve is, let's say this is C2. Or let's take C2. Okay, fine. That's fine. So this will become the closed curve now. Now C and this defining C equals to C1 union minus C2. It should be with me. What is the meaning of this negative sign here is because this is C1 is A to B, then it is coming to B to A. Okay, but C2 curve is in this direction. Okay, so minus C2 is the negative direction. So this will become the closed. This you can go in, I have taken this in a clockwise direction. You can also go for anti-clockwise direction. Okay, so that's a very first thing. And also they are non-overlapping curves. Okay, so what the line integral properties tells you that first thing is integration CF dot dr is 0 because of the given condition, because it is a closed curve. Moreover, this is integration of C1 union minus C2 f dot dr, since they are non-overlapping, this is equals to integration C1 f dot dr plus integration minus C2 f dot dr. And you know, minus C2 means you are going from B to A. When you want to go from A to B, what will happen? When you change the limit, what will happen is the negative sign will come into the picture. Okay, so this is 0 equals to this. This is equals to integration C1 f dot dr. This is minus integration C2 f dot dr. And now you are through. So this implies integration C1 f dot dr is equals to integration C2 f dot dr. Not that C2 is any other curve which is joining A2. So path independence and means integral over a closed curve. See, any closed curve C is 0. Both are the same statement. Okay, right. Until now it is. So here the statements which supports the argument just we have debated, or you can say have mentioned. Okay, not debated because we have not spoken about it. Anyways, so path independence versus conservative principle. So the first statement is I think just now we have proved. Okay, it's FBA continuous vector field defined on a domain D. Let C be any smooth curve lying in D. The line integral is path independent if and only if you have integration, this line integral along every closed curve C dash lying in D is 0, path independent, and these are the same. Okay. Now, the next result you have to take it as it is at present, because it's going to be using Stokes theorem. Okay, so that will be means our can say the last theorem for this vector calculus, Stokes theorem. That whenever we will do that, okay, then this result will be proved. So, however, what it says is if the F be a continuous vector field defined on an open connected region. So this is supported by this connectedness of the region. Okay. So what do you understand by connectedness? Have you gone through this definition? Simply connected. No.
No, sir. I don't know.
Okay. So there are various definition. Okay. But we are going to. I just want to right now give you a simple meaning here. Okay. So connectedness, openness. I think open means no boundary points. Okay. And connected means you take any, means you define any, this is a, let's say D. Okay. So openness means these boundary points are not there. The second thing is you take any closed curve. Okay. Inside this, you take any closed curve C. None of the point will be outside D. Okay. Or you can say that can be streamed to the center. Okay. Mean that can I can give you this this means there should not be any hole inside it. Okay, this is what we mean is there should not be any hole. It's like you have a paper, then if you cut a circle or a disc from there, okay, that is a simply connected. But if you cut a circle or sorry disc, because we have to mention it's a disc only, where we cannot go for a circle. So if you put inside a one small hole, okay, that it will not be a connected. Means you take any closed curve that should be straight to the center. Means you can means all the points lie inside it right now. So okay. So later on, I will give you a mathematical definition. Okay, there are various ways to look at it, like means you can they are D you can write as two non-overlapping sets such that A union B such that A closer intersection B is empty. Okay, and A intersection B closer is empty set. Okay, something like that. Okay, so I will come to that little later. Right. So what I can make you understand is by simply connected means you take any closed curve inside the domain. Every point should lie inside D. Okay. Simple curve. Okay. So what this theorem gist is here is first is open connectedness is required. Then if the line integral is path independent, then F is conserved. Right. So we will come later because it requires some supporting other definitions as well. So I'm just avoiding the here. Okay. So this will relate the path independence versus the conservative. Okay. Right. Okay. Now we have heard this word somewhere, exact differential, right? In the differential equation, right? Exact differential equations, m dx plus n dy, and we have tried to, if you recall, m dx plus n dy we try to solve this equation equals to 0, and we say that this is exact if and only if dou m by dou y equals to dou n by dou x. So this is what here first condition. So here is instead of m dx plus n dy, here is also you will have m dx plus n dy plus p dz. So in the 3 dimension, you can say. Okay. So you can say, you can recall this is nothing but f dot dr. If I writing this m dx plus n dy plus p dz. So dr, you know, dxi plus dyj plus dzk, and if you take the dot product, it is going to be m dx plus n dy plus p dz. So we say that this integral or this integrand is exact when whenever the conditions, these conditions are okay. Right. So this is what the definition of exact differential. Okay. Now here what this theorem says you that let f is, this is the vector field, this is a vector field. Now if the m, n and p, these are the functions of x, y, z. This could be possibly functions of all the 3 variables. Okay, so they are scalar valued functions. So possibly you can always able to find out the gradient fields. Okay, so if the gradient of these scalar valued functions are continuous on a domain D. Okay, so these are the conditions on this capital N, and capital B. Okay. Now, if f is conservative, then we have the following. It is very easy to establish this. Okay. So what I can feel from here, it's very easy. So what it is saying, if I say is a very, I'm just giving you the rough flow. Okay. So what it is given is the vector field f equals to mi plus mj plus ek. I'm using the abused notation here. It's m and p are the functions of x, y, z, and given that f is conservative. F is conservative. So this implies you have there exists a scalar valued function f such that capital F is equals to grade f, and that is equals to fxi, fyj plus fzk. So both has to be the same. So from here and here, so from this and this, what it implies is m must be equals to fx, n must be equals to fy, and p must be equals to fz. Now the condition that these gradients of m, gradient of n, and gradient of p are continuous. Okay, the components are continuous. Okay, how does it help you is it will help you in applying the mixed derivative theorem. If you recall, mixed derivative theorem tells you that fxy is same as fyx whenever first order and second order partial derivatives are continuous. Okay, so this is what it will help you. Okay, here the components are continuous. So now from here dou m by dou y is nothing but dou square f by dou y dou x. Similarly, dou n by dou y you can find out. So what mixed derivative theorem tells you that both has to be the same. Okay, and you have the first condition. So if you take first two, so this implies my is equals to okay, dou square f by dou y dou x is equals to dou square f by dou x dou y, and that is equals to dou n by dou x. So this will give you the first condition fy equals to nx. Now for the second one, you can differentiate dou n by dou z. and this is dou p by dou y. Okay, so that next we have this is nz is equals to dou square f by dou z dou y. Mixed derivative theorem tells you this is equals to dou square f by dou y dou z, that is equals to dou p by dou y, that is. So similarly, you will have Ex is equals to mz. So if f is conservative, you have this following condition. Okay, so it is also very easy to memorize. Okay, so you have this is m and p equals to, recall this is n p m. Now this is y z x x y z. I think this is right. It's very simple. So M and P in the cyclic form. M and P, then NPM, and then you just find out the way. I have found the following way to memorize this condition. So that will give you the exact differential. That's the meaning of exact differential. Okay. Now, so this will give you the conservative implies this. F is conservative, this implies this. Now, this will implies the conservative. Okay. So this is what the next result says, that let F equals to this be a vector field defined on a simply connected razor T, where gradients of M, N, and P are continuous. If these conditions hold, then F is conservative. Okay, so conservative means you will have the following. So now, suppose I'm just giving you the gist of the result. Okay, you have integral C f dot dr, and that is, let's say, m dx plus n dy plus p dz. Now, if you have my equals to mx and z is equals to y, px is equals to mz on D, which is enclosing this curve C. Okay, this implies there exists f such that f equals to grade f. Then you have fundamental theorem of line integrals, if you recall. So this implies integral C f dot dr for f dx plus n dy plus p dz equals to integral C grade f dot dr, and that is equals to f of x2 comma y2 comma z2 minus f of x1 comma y1 comma z. You can apply the fundamental theorem. Okay, right. So exact differential implies the conservative. Conservative implies the exact differential. So let's do some problem. Okay. Now let's do the first problem. So you have been asked to uh, okay, so you are supposed to identify or find out the line integral of the following field. So you have been given with f equals to yzi plus zxj plus xyk. Fine. zxj plus xyk along any smooth curve. Find the line integral of the field along any smooth curve it is contained. So the question itself having the hint. Okay? Along any smooth curve means it should have path independence. Then only you can talk about this. Otherwise, it is very difficult to generate every curve. Right? Now, the next thing is path independence and conservativeness also related. Okay, so you have to use that idea here. Okay? So now if you look at carefully, so so your objective first is to find out the grade f. Means your objective to find out this f. If it is there, if it exists, or if the field is conservative, okay, then you are through. Okay, now so to obtain this, you can write fxi plus fyj plus fzk. Okay, now I think so this implies I know I can analyze that because I component x is missing, j component y is missing, k component z is missing. Okay, so it can be verified. Means I will give you. It could be f is nothing but x into y into z. Okay, it is easy to verify. So this implies fx equals to, I'm just going to do this, yz. Fy is equals to zx. Fz equals to x into y. Now use the first one. So first equality, this implies f equals to f of x comma y comma z integrate partially with respect to x. That will lead to x into y into z plus some function h. It could be a function of y, it could be a function of z. Okay, constant, or it could be a function of y and z both. Because if you do function partial derivative with respect to x, you are going to get the yz. Now, use these two equations to find out this h. Okay, so from now this here, now what is fy? So what is fy is going to be xz plus hy yz. But that is equals to fy is equals to yz. Fy is equals to xz, right? Because of the above relation. So this is equals to hy, partial derivative of h with respect to y is 0. Means it is not a function of y. Y is not coming explicitly, at least. So this implies h of y comma z is some function of z only. That's a very first. So therefore, this implies f is equals to x into y into z plus g of z. Now, use the last equation. So differentiate partially with respect to z. So that's going to be x into y plus g dash of z. But, you know, from above, fz is equals to xy. So to satisfy this condition, this must be equals to this. So this implies z dash of z is also 0. This implies g of z is constant. So finally, this implies f of x comma y comma z is equals to x into y into z plus some constant. Now, therefore, now integral a to b f dot dr is equals to f at a, f at b minus f at a along any curve by using the fundamental theorem of line integral. Okay, so this constant will not matter, right? When you have f of b minus f of a, if you evaluate, so c is fixed, and that will get minus and 0, c minus. Okay. So your a point is minus 139, a is equals to minus 1, 3, 9. And B point is 1, 6, minus 2. So this is equals to x into y into z plus c. So 9 into, f of t. 6 into 1 into minus 4. So minus 24 plus c minus f of a. 9 into 3 into minus 1. Minus 27 plus c. So c will get cancelled and you have 27 minus 24. So along any curve c joining these two points, the value of this line integral is 3. Okay, right. So the question itself is having the hint that you have to use the path independence. Okay. Now, second problem is, are the following vector fields conservative? So your job is to identify whether this relation is possible or not. It's going to be for some grade f or some scalar value function. So I'm going to do any one of them. Is like let me do second one. Okay. Has 3 components. So you are given is f equals to 2x minus 3 I plus zj plus cos zk. Now, if there exists small f such that f equals to grade f, then you must have then fx is equals to 2x minus 3, fy equals to z, and fz is equals to cos z. Now this equation implies f of x comma y comma z is equals to x square minus 3x plus h of y comma z. Now, fy is equals to hy y comma z, that must be equals to z. Okay, so now this implies what? So now hy is of y comma z is equals to z. Now integrate partially with respect to y, what it will lead you, hy comma z is equals to y times z plus g of z. So this implies f of x comma y comma z is equals to x square minus 3x plus y times z plus g of z. Now fz from here, that is going to be y plus g dash of z. Right? Now fz is given to be cos z. Fz is given to be cos z. Now there is no way to proceed. I may not be able to evaluate now what is g of z. Means you need more information either, or it is something like from here, it is not possible. What I mean to say, because one side is purely a function of z, other side is involving y. Okay, it is not possible. So such f does not exist, means the field is not conservative. Okay, so from here I can conclude that the field is not conservative for the second one. Now, if you modify this example by, let's take, suppose if you modify this example, I can make it still conservative by making here changes like y plus. So then you can do something, okay? Because y plus here, so it will be y will get cancelled and you can easily evaluate g dash and then you can fix it and you can find out the conversion, that potential. Okay, but at present, this is not possible. Okay, right. So let's take the third problem now. So that the differential for this is exact, then evaluate the following over the line segment C joining the point. So see, if the differential is exact, and over the line segment C joining the point. So you can always draw a region around the C, okay, where that will be connected and all the things will be true. And you can use the fact that it is going to be a total, the field is conservative, and use all these previous result here to evaluate this problem. So let me have, so y dx plus x dy plus 4 dz. It is very easy to okay. Okay. So you are supposed to find the integral y dx plus x dy plus 4 times dz. I wish to know whether this differential is exact or not. So I have, this is m of x comma y comma z, m dx plus m dy plus b dz is y. N of x comma y comma z is equals to x. And p of x comma y comma z is equals to 4. Now to look at that whether this differential is exact or not, you have to satisfy the following three conditions. First condition is my equals to nx. Second condition is nz is equals to py. And third condition is px is equals to mz. Now, I hope now you are comfortable in differentiating partially direct. Okay. So whether this is true, so my is equals to nx. My is 1. Nx is also 1. 1 equals to 1. So this is true. Now nz equals to py. So nz is 0. Py is also 0. So 0 equals to 0. So this is also true. Now px is 0. Mz is 0. 0 equals to this is also. So this differential is exact. Okay. Now the next is, so the differential is exact. Now you can find out the potential now. F equals to mi plus nj plus pk. Even though I can at present I can straightforward also write the differential, that potential here, but let's do that practice here. Okay, so we are supposed to find out an f such that this is equals to fxi plus fyj plus fz. So this implies fx equals to y, fy equals to x, fz equals to 4. Now again, you repeat the same process. First equation, integrate partially with respect to x, that is giving you f of x comma y comma z is equals to x into y plus h of y comma z. Now this implies fy is equals to x plus h of y comma z. Now second equation will be used. Fy must be equals to x, so this must be equals to x. This implies hy of y comma z is equals to 0, means hy of y comma z is 0, means what? Okay, so f is equals to yi plus xj plus 4 times k. We are supposed to identify an f such that equals to fxi plus fyj plus fzk. Now, this implies fx must be equals to y, fy must be equals to x, that will must be equals to fz equals to 4. Now, integrate partially with respect to x. First equations, f of x comma y comma z is equals to x into y plus h of y comma z. Now, partially with respect to y, differentiation that will lead to x plus hy of y comma z. From the second equation, this equals to x. This implies hy of y comma z equals to 0. So this implies h of y comma z is a purely is a function of z only. So this implies f is equals to x into y plus g of z. Now this implies fz is equals to x into y, that's the derivative is 0, g dash of z, but that must be equals to 4. So this implies g of z is equals to 4 times z plus c. So therefore, finally f is equals to x into y plus 4 times z plus c. So such potential exists. Okay. And now, so we have find out f equals to rate of x into y plus 4 times z plus. Now what we are interested in integration cf dot dr, and you have starting point and end point given. Yes, so 1 1 1 and 2 3 minus 1. So 1 1 1 2 2 3 minus 1. It's going to be, so that's grade f is going to be f at 2 3 minus 1 minus f at 1 1. Now this is equals to 2 into 3 is 6 minus 4 plus c minus 1 plus 4 plus c. So that's going to be, so 2 minus 5, c will get cancelled, okay? So 2 minus 5 is minus 3. So this is the value of this value. Okay? Right. Now, if you have any question, you can ask.
Sir, we didn't check the condition like for
Which
exact.
conditions?
It is exact, and then some there is condition no like open connected, and then we can say as a the theorem was like that. No?
So see, what I told you is C is a curve journey from here to here. Okay, any curve. Okay, so you can enclose that curve by a reason, very simple reason. That's a, you can say very simple reason is disk. Okay, so in the case of 3 dimension, you have a sphere. Okay, did you understand? So or you can say ball. Okay, and these reasons are very nice reasons where whatever type of reason you have, whatever type of assumptions you require, you can assume that they are so nice to us. Sphere, balls, or you can say disc, okay, or you can say rectangle, triangles, tetrahedron, and so on. So these shapes are very nice shapes. Okay, so this is why it is not required. right now. Okay,
Yes, sir.
it will be required when you talk about the surface area, surface integrals. Okay, and when the specific domain is given to you. Okay, when you are simply going for finding the line integral, joining from this to this, you will always be able to enclose by a open connected region or simply connected region. Okay, with the definition will be mentioned a little later. Okay,
Yes.
so that condition is need not be be required to check here. Okay.
Okay, sir.
So this is why I have mentioned there that once that we will come to an end for Stokes theorem, then we will be more clarified with respect to the connectedness of the region. Okay. Any other question? Yes.
Sir, why here always we start with f of x, like from f of x we go from f of x to f of x y. And that,
Your voice is breaking. Uh, tell me.
is it fine now, sir? Hello.
Yes, yes, yes. Now fine.
Yeah, so why we always start from f of x, not from y or z?
Why? Why means I see you are talking about single variable.
No, in the question, we did this question like we start with like
This
uh,
this is fx equals to y.
yes, sir. We start with fxy, not with fy or fz. Or we can go.
You can, yes, 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 you can.
Okay, sir. That won't change.
Okay.
Like going with any path
No,
would
no,
be
that won't change. No, no, that won't change.
okay, sir.
Okay, that won't change. Okay, you can start with any equation fy equals to x or okay,
Yes, sir.
yeah. So see, similarly, we have done, I think, in the mdx plus mdy plus that exact differential equation also we have done the similar things.
Sir, there is one more like doubt, not related to regarding this lecture, but in
Mm.
fxy, like how to do like in the test book we saw that fxy means the first differentiating with respect to x and then partially differentiating with respect to y. So
That notation.
yes, sir, notation. There is a bit confusion. Like in textbook, it's showing the other way.
See, there are various ways to look at it. Okay, so this is why. So some textbook following this, some textbook may follow that. Okay. So what you can, what my understanding is saying that like fx means what you have dou f by dou x.
Yes.
Okay. Then how do I write those here f by dou y dou x? So there are various ways which you are looking left to right or right to left. Okay, so the in your words, I think this is fxy for the textbook. First with respect to x, then with respect to y. Is
Yes,
it
sir.
right? Left to right.
Yes.
Okay. So it's okay. So that's why what I have considered was is maybe we have not given any such questions in the problem itself. So instead, I will follow this week notation. Okay. So in the end semester exam also, I will follow with these notations rather with this, so that you should not be confused. Okay. The
Means
so there are So okay, so I'm just looking at in this way. Okay, so I what I am expecting is going to be f by x. Okay, first with respect to x, then with respect to y. Okay, this is what my following, you can say. Okay, but see why it is immaterial is because many functions. Okay, many functions for many several variable functions, that mixed derivative theorems are applicable.
Yes.
Though there are examples for which f by x is not equals to fxy, but still the class of functions where both are same is a large.
Okay.
So this is why it becomes sometimes immaterial whenever mixed derivative theorem is applicable. Okay, means suppose you have a nice function which is you can easily visualize, you can get intuition that you can differentiate as many times as you wish. So automatically mixed derivative theorem come into the picture. Okay.
Yes. Okay. Thank you, sir.
Yeah. Right. So again, I'm telling you that as that connectedness, again, if you want to visualize it, you take any piece of paper, okay, you cut in any shape, but there should not be any hole in between. If you put multiple holes or a single hole, that will not become a connected. That will be multi-connected. There will be multiple connected regions. Okay, so any shape without a hole can be treated as or can be called as connected. Okay, simply connected. Okay, so and you will have that orientation, that boundary, that if you include the boundary, it is a closed, or if it does not include the boundary, it will be open. Okay, so if you put the holes, it is becomes in multiple connected, not a simple connected one. Okay, though you can, what you can do is you can make it. Can you give an idea? I just want to know that this is multiple connected now by my definition, because I had put a hole. Okay, can I make it a simple connected? Is there a way to make it simple connected and I mean, so that the results can be applied? Just go by definition. You want to obtain a shape, okay, which does not have any hole. Can anyone have an idea? Suppose this is a piece of paper, okay, and there is a hole. Can I make it make some here adjustment so that new shape will not have any hole? It's very simple that you cut it. So once you cut from here to here, you will you can so this is full. This will be a shape now. There is no hole. This because this will be open now. Okay. So the reason is like this. Okay, means you are coming like this, and then you are going here, and then. Okay. So if you you have here, I just make one more line. Okay, so that we see this is a cut here. Okay, after cut you don't have this. Okay, this one is removed. Removed means you make a single cut here, but means when you open it up, means it's a open space, not a there's no cutting, only one cut is there. Okay, so it is going. This is a curve, and you have a domain. You will obtain a domain like this. This is simply connected. So similarly, if you have a multiple holes, you can also try to identify the paths so that you can make it simply connected. Okay, right. So we are okay, fine. So I think time is over. So the next lecture we are going to learn a very important result. Okay, in vector calculus, which is known as Green's theorem. Okay, and which will give you uh, some real life application, like in terms of if you want to find out outward flux, how much flow is fluid, okay, or how much work done is happening, or it also relates line integral to double integral as a okay, line integral to double integral. Okay, then the situation may be more simple than the case for line integral, or you can go with the reverse also. Double integral also can be converted into line integral. Okay, so this is this okay, result we will see tomorrow or maybe day after. Okay. Yeah. Okay, then fine. Thank you.
Thank you, sir.
Thank you, sir.
Okay, sir.